So this is the two constraint situation. So you can see here, there's really just another layer going on here. So you have to optimize the function, blah, 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 blah. We have the two constraints, g of x, yz is equal to 0, h of x, yz is equal to 0. I just wrote it in terms of the function of 3 variables, but it could still be functions of 2 variables. I mean, it's just the number of constraints that you have. What we're doing is we're introducing a new multiplier. We have our lambdas down the line here as creating the proportional relationship, but we also now have a mu, all right? So that mu is just another multiplier, a coefficient that allows, if it were just a one constraint, it would allow h of xyz to become f of xyz, a sub xyz, all right? So we're combining them together into one massive set of constraints, and that allows us to get done what we need to get done. So what we're dealing with here, you know, it kind of looks it's sort of funky, but you know, you saw in those problems that we had already tackled with Lagrange that we do tend to run into situations where it's kind of hard to visualize with just images. You kind of need dynamic imagery in order to be able to get a really true sense of this. So what I did was we got a plane and a paraboloid. Now, we haven't really talked about different types of surfaces. We'll get into that with the third tech assignment, which I'll talk to you about next class. But they have names, the different surfaces, or at least the popular ones. One of them is a paraboloid. I kind of had faith in your ability to say, oh, paraboloid kind of looks like and sounds like the word parabola. I wonder if it's the same thing. Same thing with ellipsoid and hyperboloid. You know, pretty safe bet that those are just the three-dimensional versions of the thing that you know and love from 2 dimensions. And that's exactly what it is, all right? So we have x plus y plus z equals 12 is a plane and the paraboloid. They intersect and they form an ellipse. That's the first diagram from GeoGebra. Then I used the net diagrams to kind of give a different perspective and show how that slicing was happening. What we want to do is find the point on the ellipse closest to the origin. So that's that extra layer that we have going on here, all right? So we want the point on that ellipse. So what I did was I kind of trimmed it down and said, okay, instead of looking at the paraboloid, let's just focus on the ellipse itself, all right? So, you know, it's gonna be hard to see as I do this, but let me go brighter. Do a nice bright green there. This ellipse here, if we just focus on that, we're really saying, okay, we got this ring kind of floating out in space. That's corresponding with the intersection of the plane and the paraboloid. All right, so those are the same thing. What I did was I just kind of stripped away all the extraneous stuff. So if I were to say, here's, you know, a stick of butter, here's a knife. And you can cut it at different angles, cut it straight down, cut it at an oblique angle, whatever. Then you look at the cross section, but then just take the frame, the outer frame of it, you know, the perimeter of that cross section, and just look at that. It would be along those lines. So just imagine that stick of butter was a paraboloid of butter, and then you'd be in pretty good shape. All right. Now, what the sphere gives you, you look at that and you say, well, you got a sphere just kind of came out of nowhere. Well, we're talking about the distance between the origin and a point in space. All right. So the origin's tucked away in here. What I need is the distance between that point and some point along that ellipse, the one that's closest to the origin. All right. So the way the distance formula works, distance is equal to the square root. We talked about this, I think it was last class. We'd have x minus, if we wanted to keep it in general terms, we would say x minus x sub o, you know, I think that's what I used to keep it variable, plus y minus y sub o squared. I meant to say squared for the x minus x sub o also. I wrote it, but I didn't say it. Z minus z sub o squared. All right. Now, if I clean this up, and by cleaning it up, I mean, you know, just square both sides. I get all this stuff again, just without the radical. And last time we talked about this as a strategy for just kind of making our lives easier, which is fine. But really, if you kind of look at this carefully, you see that what we're really dealing with here is an equation that's in the form, the same form as the standard form of a sphere. All right. So the distance formula can also be, you know, just in two planes, not two planes, in two dimensions, can be thought of as the radius of some circle, some arbitrary circle with the form of x minus x sub o squared plus y minus y sub o squared equals r squared. All right. In three dimensions, the standard form of a sphere and the distance formula related to a sphere would be the same idea. All right. So what we get here is a function. It's a function of three variables. And we know from the problem that we did last class, the one where we talked about the distance from a point to a plane, a point in space to a plane, that as the distance squared goes, so does the distance. So if we minimize the distance squared, we'll also be minimizing the distance. All right. So what I can do is I can call this f of x, y, z. Poor quality z. That's going to be equal to all of this stuff. So I'm just calling this function. It is a function of three variables. Now you say, well, what about the x sub o, y sub o, z sub o? We'll get to that in a second. Hopefully we'll be able to swap those out. All right, let me resize a little bit. Change the coloring for consistency. So we have a function. We got something to work off of here. All right. Now, we do know that that point on the ellipse is going to be variable in some capacity. But it does have to have on the other end of that distance, it has to be at the origin. It has to have the point 0, 0, 0. All right. So I would let that, if that's visible, I think it is, be x sub o, y sub o, z sub o. All right. So this whole thing is going to collapse down very nicely. Just nicely. Let's not oversell it. Just nicely. X squared plus y squared plus z squared. All right. So that's the function that we're trying to minimize. Now we just got to think about the constraints. All right. And fortunately, there isn't really too much in the realm of thinking that needs to happen, right? Because they gave us some information to work off of. So this is, again, I'll just make a note. We want to minimize this. All right, so function to be minimized. That's supposed to be parentheses around it. So let's talk about the constraints. All right, we have two possible constraints, and they just flat out gave them to us. They're determined based off of the plane, x plus y plus z equals 12. If I bring the 12 over, it becomes x plus y plus z minus 12 equals 0. All right, so one set of boundaries or one set of constraints are determined based off of the plane, which I can now call, pick your poison, I'll call it g of x, y, z. Because it doesn't matter which one you call G and which one you call H, because they're both going to factor into the problem anyway. So it's entirely up to you. And I'm going to go red for those keeping score at home. So the next constraint is the paraboloid, z equals x squared plus y squared, which I can modify and call that x squared plus y squared minus z is equal to 0, which in turn would now become h of xyz is equal to x squared plus y squared minus z. All right, so those are my constraint functions. All right. All right, so I didn't give a whole heck of a lot of space for this, so time to do a little shrinky dinking. I'm still going to leave that over on the right-hand side, though. All right. I'm going to get rid of some of the stuff in Desmos because it's just going to get in the way. And I'll reorient it. All right, so let's get, and maybe I'll just pop it kind of right in the middle here. I'll get all of my partials out of the way right now. All right, so we're going to have f sub x, f sub y, f sub z, if I can speak, which it's debatable. So f sub x, 2x, f sub y, 2y, f sub z, 2z, g sub x, 1, g sub y, also 1, g sub z, you guessed it, 1. And then h sub x, 2x, h sub y, 2y, h sub z, -1. So those are all my partials. I'm partial to my partials. Just kind of jot it down here. These are partials. All right. Now you can refer back to the model at the top, but it's basically saying that my first order partial with respect to x, y, and z for my optimized function, or the function to be optimized, is going to be equal to a constant multiplier, or a scalar multiplier, or arbitrary multiplier, whatever, lambda, multiplied by g sub x, y, and z, plus mu multiplied by h sub x, h sub y, h sub z. All right, so it's really just these three different levels all working in concert with one another. So just a question of where we're going to put all this stuff. I'll just tuck it down in the right-hand corner over here. So we're looking at 2x equals 1 times lambda. You don't have to write the 1, obviously, plus 2x. Well, I'll say mu first, just to keep it consistent with the model. Lambda times 1 plus mu times 2x. 2y equals lambda times 1 plus mu times 2y. And then 2z is equal to lambda times 1 plus mu times -1. All right. So that's a lot of information, but we're getting there because we have 3 equations with more than 3 variables. But the idea here is that somehow, some way, we should be able to get a solution out of this. Right? You look at it and say 3 equations, 3 variables, but we still have our constraints. Those constraints, the outer boundaries, are set equal to 0. All right, so I'm still working off of use this tool. We still have these that we can come back to. They relate x, y, and z to each other. All right, so I can just kind of do a little copy paste job here and get those into the party.
Professor? Hello?
An extra y. I knew it was going to come along for the ride. All right. So now I have 5 equations with
Professor?
5 variables. So I know it's a matter of time before I get the solution out of this. It's just a matter of what that solution is going to look like. All right. So let's kind of play this carefully. And let me resize this. It's going to bug me. Going to move that down there. I'm going to give this the more prominent role here. Center stage. All right. So let's take a look at the first equation, basically. All right. So let's bring it in here. Take a look at this guy. So I can clean it up. There's really not much to clean up, but I do have 2 terms, each consisting of a 2x. So let's get those over to the same side. So I'd be looking at 2x minus times 2x is equal to lambda. All right. So that's something. You know, so it's a matter of, okay, well, what do I do now? Well, I have a common 2x. That's kind of the reason why I brought it over. So let me factor out that 2x. I have 1 minus mu, and the whole thing would be equal to lambda. All right. So I got that part. That's fine. Just double checking something. Yeah, no, it looks good. All right. So then I could do the same thing, it looks like, with the y's. So 2x minus mu times, I'm sorry, good geez. It's like right in front of me too. Minus mu times 2y is equal to lambda. Common 2y that can be factored out. 1 minus mu is equal to lambda. And then you kind of look at it and say, okay, well, what does that tell me? Well, if you look at these 2 expressions, you know, we could do it algebraically, but if you really look at them carefully, you see that the only thing that differs from one equation to the other would be the variable here. Now, maybe you don't see that. Maybe you do, maybe you don't. Maybe you saw it a lot earlier. Maybe that would be even better. All right, so what I'll do is I'll really drive it home. They're both equal to lambda, so they're equal to each other. So I could say 2x, 1 minus mu, 2y, 1 minus mu. I can cancel the 1 minus mu's and the 2's, and I'd be left with x equals y. So I have that relationship where x and y are the same. Right? That's great news. I just canceled, I really kind of streamlined things. That's wonderful. All right. I can cancel the 1 minus mu's because mu is a constant. All right. I'm not losing a variable in the process. It's not like I'm having an extraneous variable kind of situation going on here. All right. So then now I can start thinking about another form of substitution. But if my goal is to come up with a solution to a system of equations, now I have these 2 guys that I can work off of. Because in both of those equations, I can replace either the x with a y or the y with an x. So I can say, and let me use purple. So I have x plus y plus z minus 12 equal to 0. Oh, smidge that over a little bit. And now I know that x and y are the same thing. So I can now say x plus z minus 12 equals 0. So that gives me z is equal to 12 minus 2x. If I want, I can solve for x too. It really doesn't matter. For the other one, let me just draw a little line segment separating. I'd have, like, I'm starting with x squared plus y squared minus z equals 0. So x squared, since I know y is the same as x, plus x squared minus z equals 0. So now I'm looking at z equals 2x squared. All right, so 2 equations, 2 variables, straight up substitution, and I'll have the value of x. All right, now I was mentioning this, well, this would be the third time between last class and this class. Let me just move this a little bit further up. Third time between last class and this class that you need not do something like this algebraically. That's why I cleared out my my Desmos here. What was that noise? Some kind of an alarm. 12. I'm using y and x, but still. So y equals 2x squared, and I'm just looking for the intersections. So instead of it being x and y, it's x and z, but still, we'll get intersections between these two. So we'll have 2 out of the 3 variables solved for, and the other one we know is already equivalent to x. So x comma z is equal to, I gotta bring it in, sorry. Handwriting, when I try to do it too far away, the handwriting gets just too bad. All right, so x comma z would be negative 318 and 28. All right, so since I know that x and y are equal to one another, I can now conclude that the ordered triples, so therefore we're talking negative 3, negative 3, 18, 2, 2, and 8 for x, y, z. Now, ultimately, it says find the point on the ellipse that's closest to the origin. All right. Now, this is optimization. We could be maximizing, we could be minimizing. I don't know which one's going to be closest. I don't know which one's going to be the furthest. So there's a couple of ways that we can handle it. One would be to go to GeoGebra and pop that information in. Another way would be, like plugging and chugging. In this case, plugging and chugging won't be too bad because the plugging and chugging has to do with the distance formula, which was distance from the origin. So x squared plus y squared plus z squared. All right, so that's not too bad. So I would just do a squared plus b squared plus c squared and create sliders for all those. Drag this down and just move those sliders to wherever I want them. In this case, I'm just looking for the distance. Well, this would be distance squared, but still it's a basis of comparison. All right. So when I look at this, I would say, okay, well, what does that give me in terms of d squared? So negative 3, negative 3, '18's a little bit beyond, so I'll just type it in. So that's 342. That's the d squared. So the square root of that would be the actual distance. But again, wherever the d squared goes is where the d is going to go. So I can make my C value an 8 now. We're looking for 228. So kind of need like a soft touch, but really just kind of like a cling-free touch in order for this to work on a touchscreen. All right, anyway, 72. So d squared is much bigger for -3, -3, 18. So that's telling me that that's going to be the point on the ellipse that's furthest away from the origin. This one here, if I can time my statements with my actual movements, this is going to be the closest to the origin. All right. So yeah, a fair amount of work when it comes to these kind of questions, but you think about the second derivatives test. There's definitely a fair amount of work involved in those too. So there's no ifs, ands, or buts around it. You got, just kind of buckle up and get to work. So let me stop that recording. Okay, so I got 13 chats coming in. So let me see. I missed all those.